Hello, everybody. Today we are going to be talking about, it's loading, function inverses. So this will be exciting. I don't really love the way that this lesson is kind of brought to you. So if you have some questions, I want to make sure that you get those asked and answered. But let's see what we can do here. Just as a warm-up, we have a little function here for you, and they want to know what the domain is. Well, don't forget, the domain of the function is what x is allowed to be. So for this case, we could say the set of all x such that x equals -4, -2, 0, 2, and 4. We're not going to assume that there's points in between there, although there probably is. When we figure out what the range is, that's what the f of x values are, or the y values. Set of all y such that y equals, what do we have here? -2, -1, 0, 1, and 2. This is definitely a function. There is function notation for starters, but if you look here, none of those x's repeat. So what is the rule? Can you figure out what's happening? How did I get from -4 to -2? Or -2 to -1, or 0 to 0 and 2 to 1? The rule that's happening is here, they're taking that x value and they are dividing it by 2, or they're taking 1/2 times the x value. Is it 1 to 1? Well, does each y only have one x? It does look like it is 1 to 1. This would be the graph of a line. If we were to graph it, it would be kind of a flatter line, and it passes the horizontal line test as well. Okay, by the end of this lesson, we're going to talk about finding the inverse and verifying that functions are inverses. Okay, so what is an inverse? What are we even talking about here? Well, inverses undo a function, okay? So what it does is it takes our table, and instead of having an x, f of x, they will flip-flop it. Now, the way I used to teach this, and I liked it a little bit more, is we looked at a real-world example, and we were looking at various speeds, and we were looking at skid marks on the concrete or the road for a certain car based on going, I'm making this stuff up. So you're going 20 miles per hour. Maybe it left like a 10-foot skid mark. And if you're going 30, it left a 16. And if you were going 40, it left a 22 skid mark. And I'm totally just making this up. And that was bad because it was linear and I didn't want it to do that. Like 25 feet. So we had this table for speeds and skid marks. And we talked about how they probably created this table was by doing various test trials and a test track or something. Well, when the police come and they investigate a crime scene or an accident, they can't tell how fast a car is going. They, in fact, can only measure the skid mark. So they would have a table where they would want these all flipped around. They would want the skid marks here, and they would want the speed here so they can determine if the car is going too fast or not. So they could do the measurement of the skid mark and type it in their computer, and it would take the speed. This table undid this table. In inverse, the first thing you need to know is that basically the x and y sides of a table switch. So if I asked you for an inverse for this guy, you would just switch all these ordered pairs to -2, -4, -1, -2, 0, 0, 1, 2, and 2, 4. In other words, the domain and the range switch. So the domain becomes the range of the inverse. So the domain of the function, I should say, becomes the range of the inverse. The range of the function is the domain of the inverse. So you could look at a table, or you could look at a domain and range and switch, or here they just have ordered pairs and they just switch the x and y. All you're going to do is switch the x and y, and that's the first property of inverses because they have multiple properties. The first one is that they undo each other. And the second one is the x and y's are switched, which Also can be said, some people think of it as a third property, the domain becomes the range and the range becomes the domain. So when I say undo each other, let's talk about our function x divided by 2. If that is the function, how can I undo dividing? The inverse could be x times 2 or 2x. To undo dividing by 2, we could multiply by 2. And if you look, negative 2 times 2 times 2 times 2. You can find a rule for going the opposite direction. Now, little one-step problems, that's not a difficult task, but when we get into some two-step problems, it's kind of surprising what the inverses would look like. And we're going to introduce some inverse notation as well. So this is the inverse, I guess. I didn't double check. So did we switch to ordered pairs? No. -4, -2. This is the same. Now they're asking what would the domain of the inverse be? So the domain of the inverse, and the way we can write this is f -1 of x. That's called the inverse of f of x. The -1 does not mean to the negative first power. This is just a notation. The inverse of x, what would the domain be? Well, the domain of the inverse of x would be what the range was of the original. So it's a set of all x such that x equals -2, -1, 0, 1, and 2. So given an ordered pair that is on this inverse, all I'd have to do is switch the ordered pair. So 2, 4 would work. Or you could put 1, 2, 0, 0, -1, -2, or -2, -4. So this inverse notation, like I just said, we're going to use this f -1 of x. Sometimes we just use regular function notation and we label it as a function, and its inverse would be called g, but g could also be called f inverse of x, like that. So having the function of having is inverse would be doubling. So what would f of 6 be? Well, that's telling you to go to function, f, take out the x, and plug in a 6. Half of 6 is 3. F of 6 equals 3. Well, because of that, I also know what f inverse, not of 6, but of 3 would be. If f of 6 equals 3, then on the inverse, if I plug in 3, I should get 6, because 2 times 3 is 6. So if you have a function and you know a value, you can switch it to find its inverse. So let's look at this notation. What is this talking about? Okay, so f of 6 was half of 6. Well, half of 6 was 3. F inverse of 3 gets you back to the 6. I want you to think about that. What if I would have said f inverse of f of 8? Half of 8 is 4. What's f inverse of 4? 2 times 4 is back to 8. My pen is skipping out on me. How about f inverse of f of 10? Half of 10 is 5, but when I double it, I get back to 10 again. So every single time when I do one after the other, or one follows the other, I get what I started with. So why does that happen? Because this function is doing something. The f inverse is undoing what was done. So what are you left with? Just whatever you plugged into the function. So if you have your machines, here's function f. F inverse undoes it. So no matter what you plugged in, at the end of the day, it's going to shoot it back out. It's like a funnel. If 4 goes in here, 4 is coming out. If 10 goes in here, 10's going out. If x goes in here, x is going out. So what we say, and this is another property of functions, is f inverse of f of x equals just x. One function does something, this one undoes it, and basically you're just left with a funnel, and this x just keeps sliding on through. Okay, so you can also write that as f of f inverse of x, because you could write it in the opposite way, and that's how you can tell if functions are inverses. So let's do a little math on the problem we already looked at to see what that would look like. So we know these guys are inverses. F of x is 1/2 x, and you know that g of x equals 2x. You know that they are inverses. Now we can show it because I can do f of g of x, which would be f of 2x, which tells me to go to function f, take out the x and put a 2x, and I get x. Because f of g of x equals x, we know they are inverses. That's a way to check to see if functions are inverses. Here's another example. Let's look at these using that same idea. What is f of 2? Half of 2 is 1. So what's f inverse of 1? F inverse of 1 would bring us back to 2. So f inverse of f of 2, one thing does it, the other thing undoes it, and we're just left with 2. F inverse of -2 takes you here. That gets you -4. Take that answer and plug it into this guy. Half of -4 is -2. And f of f inverse, something happens, something undoes it, and you're just left with -2. So once again, you might want to write that down. F inverse of f of x is the same thing as f of f inverse, and what that gives you is whatever you're plugging into your machine. And if you're not giving a specific number, we just get the x. Okay, let's check and see if these are inverses. So let's look at these first. They're giving me ordered pairs, so we just need to see if everything flip-flopped. So far, it looks good. Everything looks like the x's and y are switching. So are they inverses? The answer is yes. How about this? Is adding the inverse of subtracting in this case? Well, if you can't tell, you can do f of g of x. That would be f of x minus 7. Go to function f, take out the x, plug in the x minus 7, and it's x minus 7 plus 7, which gives me x. So these are inverses. You can do the other way as well. G of f of x, because you need to do both. That would be of g of x plus 7, which would be x plus 7 minus 7, which also gives you x. So yes, they're inverses because they undo each other and they leave us just with x. Let's look at this. Are these guys inverses? Well, 2, 3, 3, 8. Well, look here. If 3, 8 is on this graph, what's supposed to be on this graph? That's supposed to be 8, 3 if they were inverses. 2, 3 is here. That's supposed to be 3, 2. The only thing that this graph did was just rearrange the way they put these. They did not switch the x and y. Those are not inverses. Okay, so what do the graphs of inverses look like? Because this is another property of inverses. Let's graph 1/2 x. So I rise 1, run 2, rise 1, run 2. Okay, and we have a kind of flat line like we talked about. Okay, now if I graph y equals 2x, it rises 2, run 1. I don't know if you're going to be able to see this relationship or not, but there is a relationship between inverses. Okay, they do reflect over a line, and the line that they reflect over is right there. That's the line y equals x. Because the ordered pairs switch, they reflect over the line y equals x, and that's another property. Graphs and their inverses reflect over the line y equals x. And there's two ways you can do that. Some kids have a hard time seeing that reflection. So the other thing you can always do is just switch the ordered pairs. And that's what we'll do on this next one. So I have 2x plus 2. y-intercept's 2, slope it out. We're going to find the inverse. I told you if there's more than one step, sometimes it's a little bit tricky to find the inverse. So what I'm going to do is in blue, I'm just going to switch the ordered pairs. 0, 2 becomes 2, 0. 1, 4 becomes 4, 1. -1, 0 becomes 0, -1. And -2, -2 still is -2, -2. So what is the equation of this line? Well, it's y equals, the slope is 1/2 x minus 1. That might surprise some of you. You might wonder, what about that 2? Well, it's because that inverses don't always look the way you expect them to. And on the next slide, I'm going to show you how we can find the equation of the inverse if you don't want to switch the ordered pairs and graph, how we can do it with algebra. Okay, well, I guess in the next slide, because first we're going to practice some more. So which graphs are inverses? Can you tell if they reflect over the line y equals x? Now, Mrs. Bruno can't. She doesn't do very good at that. But I would take some points and flip it around. So on this purple graph, I have 0, it's going by 2's, 0, 4. So that would go here with 4, 0. And it looks like the purple and the orange are inverses. These guys are related. They reflect over the x-axis, but that's not what we're looking for here. Now, how do we find the inverse with algebra? Here's what you need to know. To find the inverse with algebra, if you don't want to graph it, here's what you do. You switch the x and y, and you solve for y. Okay? Switch x and y and solve for y. So I'm going to go back to that problem that I just did with you, that we looked at the graph and did, and switch x and y and solve for y and see what happens. So our first equation was y equals 2x plus 2. I'm going to find the inverse by switching the x and y. X equals 2y plus 2. And now I'm going to solve for y. So I'm subtracting 2. X minus 2 equals 2y. Divide everybody by 2, and that's where that 1 came from. That's 1/2 x minus 1 equals y. So if this is the function, and we'll call it f of x, then the inverse, or f inverse of x, would be 1/2 x minus 1. And that's how you do it with algebra, but you could also do it with the graphs. So let's try this guy. F of x is -4x minus 8. So we're supposed to switch the x and y and solve for y. Well, there's no y here, but you know f of x can be written like this. So now we can switch the x and y and solve for y. To get y by itself, you would first add 8. And you get x plus 8 equals -4y. Divide each and every piece by -4. And you can leave it as x over -4, or you could change it to -1/4 x minus 2, and that equals y. Or you can write equals f inverse of x. Okay, it says select the equation, but I got rid of the choices, so we're just going to find the inverse. So what is the inverse is what we're going to do. So we're going to switch the x and y and solve for y. So now it becomes x equals y minus 3 over 5. To get the y by itself, we're going to multiply both sides by 5 first. So that's 5x equals y minus 3. Then add 3 to both sides. And 5x plus 3 equals y. Or f inverse of x is 5x plus 3. Keep in mind, this guy could also be written like this. F of x, if you love math, 1/5 x minus 3/5. So like I said, when there's more than one step, sometimes the inverses look a little surprising. But if you graphed it and switched the ordered pairs, you would see that they are inverses of each other. Here's some more. Are these guys inverses? We got here some points switching. What's this? Over 0, over 1, up 1. These aren't even inverses, are they? What the? This is not even right. So this is not inverses. You can tell because the 0.0, like up 0.25, should be at 0.250. These are not inverses. So I don't know why it said inverses examples. If I wanted to find the inverse, I could. 6x minus 3. This isn't even graphed right. I don't know what the garbage is here. It says going by 1, so negative 3 would be right here. Rise 6, run 1. That should be like that. I don't know what's happening here. And then switch the ordered pairs, or we can just do it by hand. X equals 6y minus 3. X plus 3 equals 6y. Divide everybody by 6, and it would be 1/6, a little glitch. 1/6x plus 1/2 equals y. That's what should be happening. But they would both be functions. But what happens here is that they're not both functions. The orange graph is y equals x squared. When you switch the ordered pairs, you get a sideways parabola. So they took 1, 1 and switched it. They took 2, 4 and switched it to 4, 2. And then this. These are inverses, but the blue graph is not a function, and that's important. Sometimes inverses are not functions. So we have to do something to make it work out for us. So here's what you need to know. You can graph any inverse of a function. You just have to switch the ordered pairs like we did. But sometimes the inverses are not functions like that one. And there is a way you could tell if we go back. If a function's inverse is a function, it would have had to have been 1 to 1. And we talked about that on our last test. Because this guy is not 1 to 1, when you switch the ordered pairs, it will not be a function. So only 1 to 1 graphs have inverses that are functions. You still have an inverse, but it's not a function. Okay, so only 1 to 1 functions have inverse functions. So it has to pass the horizontal line test, the original guy does, in order for it to be the case. And what we can do is we could take like your parabola we just did, and if I want to use the notation of f of x equals x squared, and I want to know what the inverse is, and I want to use function notation like that, then first thing I'm going to have to do is say, hey, only look at half of the graph. X is greater than equal to 0. So we're not even going to look at this side, and that allows us just to look at this much of the graph. And then you can switch the x and y and solve for y. And y can be the square root of x, or f inverse can be the square root of x. If you did not do that and did not say half of it, it would have been plus or minus the square root of x, which is why it's not a function, because it would technically be two functions. Okay, we will have some more practice with that as we go on. So let's decide if the inverse would be a function or not. This guy is a function, but is its inverse a function? No, it's not. We can find the inverse still. We can graph it. Switch the order pairs. 0, 0. 1, negative 1 becomes negative 1, 1. 2, negative 2 becomes negative 2, 2. 3, negative 3 becomes negative 3, 3. Okay, so there's one piece. Now let's switch these ordered pairs. Negative 1 still is negative 1, negative 1. Negative 2 still is negative 2, negative 2. So that blue graph is the inverse, and you can tell that it is not a function. How about this guy? Will his inverse be a function? It is a function. The inverse will also be a function because it passes the horizontal line test. And we could graph it by switching these ordered pairs again. This one's going by 2, so 0, 1 becomes 1, 0. What's here? 2, 8 becomes 8, 2, which should be about here. Negative, this must be supposed to be an 8, I guess. These graphs are not very good. Okay. -6 is like up to 0, becomes almost a little up 0 down to 6. And you could tell that this graph is going to kind of go like that. It kind of looks like it might not be a function, but it is. Okay. This is a function. Its inverse will also be a function. You could tell because it passes the horizontal line test, and we could draw it by switching the ordered pairs. 0, 0 would still stay in the same spot. 1/2, -1/2 would be -1/2, 1/2. 1 is like down 2, be like -2 up 1, so kind of like this. And then we could switch these. -1/2, 1/2 would be like 1/2, -1/2, and it's going to kind of go like this. Okay, again, switch those ordered pairs and you can figure it out. Sometimes it's harder to see than others. Okay, last example, I think, of when we'll be using an inverse. You have a formula for Fahrenheit to Celsius. You've seen this before. You plug in the Celsius and you'll get a Fahrenheit. Now we can find an equation to go from Fahrenheit to Celsius, okay? So you can find an equation by finding the inverse. So the inverse of this would be what? Well, we're going to switch the x and y and solve for y. So in this case, we're going to switch the c and f and solve for f this time. So -32 minus 32. So c minus 32 equals 9/5. Actually, I don't want to switch the c and f. This is going to make it confusing for you. We're just going to pretend it's x and y again. And we're going to switch the x and y, and we'll put in the stuff in a minute. X equals 9/5 y plus 32. So subtract 32, x minus 32 is 9/5 y. And then you can multiply both sides by 5/9. Now, when you do that, you will need parentheses. So that'll be 5/9 times x minus 32. And that will equal the y value. Now, earlier we were plugging in Celsius to get Fahrenheit. This would be plugging in Fahrenheit to get Celsius. So that'd be 5/9 Fahrenheit minus 32 equals Celsius. Okay, is f a function? This first guy, yeah, it is. Is it 1-to-1? Yes, this is a graph of a line. So that means c would be a function, and c would be 1-to-1 as well. Okay, I think that's it. I'm pretty sure anyway. Nothing's happening when I click. So that will be it for inverses. Good luck on your quiz.